All right, welcome to the next video. So we talked about Kepler, we talked about Newton. Now we're going to combine the two a little bit. So we'll talk about the connection between the two. We'll talk about energy in section 7.4. And part of section 7.5 has to do with escape speed, so we'll talk about that part. But we'll leave, well, I'll talk about it later in the video, but I'll leave a little part of 7.5 for another video, and also talk about some a relevant Taylor series expansion. So basically in another video, we'll talk about how energy relates to the MGH that we've seen before for gravitational potential energy. So if you look at this example problem, this has to do with energy, and we won't be able to use MGH for this problem. We cannot use that one. So we'll see why that is in a moment. Okay, so your book starts off saying, well, so Newton, so before we go back to Kepler, Newton says that the gravitational force, it has magnitude g m1 m2 over r squared, g m1 m2 over r squared, and this is radially inward. So with the vector sign, you might want to put a minus sign here, and then maybe a r hat. So your book calls this ER, E sub r. So this is radially so I have in mind some really massive thing that stays at the origin because it's so massive, and then some lowercase thing m. And this isn't necessarily a circular motion. Okay, so maybe this isn't going like tangent to a circle, but it starts moving off this way at some general initial velocity. So what Newton's laws say to do, from Newton's second law, the sum of the forces is mass times acceleration. So this is equal to the mass times the acceleration of that mass. And so this tells you exactly what the mass is going to do next. So this is a differential equation. And if we were smart enough, we could solve it. It's not easy at all. Like, I don't know how to solve this right away. This is tough. This is a really tough equation to solve. Differential equation, in principle, we could solve. In principle, I think, is this an AL or an ELE? In principle, we could solve. So your book mentions that you do this in an upper division course. It's not easy at all. So we'll save this for an upper division course, how this works out. And you can prove that the orbits take on, so the motion, so this thing over time takes on certain shapes, like could be an ellipse. So it turns out there's a connection to energy. It depends how quickly this mass is moving right here and how far away it is from that mass. If this thing isn't moving fast enough, you can show that this is an ellipse. And if it's moving too fast, it actually undergoes hyperbolic motion. So it's a hyperbola. And then if you're right in between the two, it's actually a parabola. So you'd go once around the mass, and then you would just barely have enough energy to escape. That would be parabolic motion. But that's not at all obvious, right? That's tough. So we have Kepler's three laws, and we want to understand them a little better using Newton. So Kepler has three laws. The first one is actually the hardest one to prove, the elliptical orbit. So what I just mentioned about solving this differential equation and showing that the orbits are ellipses for certain energies, this is the one that's hardest to prove. And this is the one that we're actually not going to prove, even though we can prove the other two pretty easily. So Kepler's three laws, the first one, it's the easiest one to state. Planets just move in ellipses around the sun. It's the hardest one to prove. So we'll save that, just like your book says. Even centuries later, I find this class in advanced mechanics quite an effort. It does take quite an effort to solve that. The second one we proved in another video. So proven in another video. So if you haven't watched that one already, there's a video called Acceleration in Polar Coordinates. So the first half or 2/3 of that video, we're just talking about kinematics. And then at the end, we combine what we know about the acceleration in polar coordinates with just a couple facts from Newton, which say that the force is radially inwards and the force is proportional to acceleration. And that lets us prove Kepler's second law, the equal areas in equal times pretty quickly. Remember, Kepler's second law says that dA dt is a constant. So the rate at which you sweep out area is constant. So that was in another video. The third one is what we're going to do right now in this video. The t squared is proportional to a cubed. T squared is proportional to the semi-major axis cubed. So we can actually find out what that constant proportionality is. So we can derive what this constant is. So it's going to look like we're only proving this for a special case, and that is a circular orbit. But it turns out that's okay, because so that constant is true for anything orbiting like some central mass. So say you have Pluto right here that looks like this, and then you also have like a perfect circular orbit around this thing. Okay, so both of those have the same constant in front right here. So we'll call this C, a cubed. So a for Pluto, this right here is 2a, the semi-major, or the major axis length, 2a. So that a could change depending on the orbit, and your period will change correspondingly. But the c is just going to depend on capital M, and so to derive c, we can just look at this circle. Right? Maybe I'll draw a bigger circle. So we're gonna look at a circular orbit just to derive that constant. So we can derive what this constant is by looking at a circular orbit. And the reason for that is we know a lot about circular motion. But the result is general. Results will be the same constant. Same C for ellipses, for more complicated shapes. Okay, so how are we going to do this? We have some mass, lowercase m, orbiting this thing. Okay, lowercase m, let's say it's moving with some speed v. And the reason we want to look at a circle is that this a, the semi-major axis length, is really easy. It's just the radius. A is equal to r for a circular orbit. Okay, so we want to relate, the goal here is to relate the period of motion, the amount of time it takes to go once around the circle, with the radius of the circle. All right. So v doesn't appear here at all. So we might need v to write an expression for this variable. We might need v to write an expression for the radius, but we don't want our answer to depend on v. Okay, so I just introduce it here as something to work with, but we want to rewrite this expression. T squared is something times r cubed. And we want to find out what that something is that doesn't, not involving v at all. Okay, let's write down some things we know here. Okay, so t is the amount of time it takes to go once around the circle. So the speed of the object is the distance divided by the time. So the distance it moves around is 2 pi r, the circumference of the circle. And for that distance, it takes a capital T amount of time to do it, right, the period. Okay, so this will be one of the two equations that we'll use, that we have to play with. Okay, the second equation comes from Newton's laws. So remember, we're using Newton's laws to prove Kepler's stuff. And so Newton tells us exactly what the force is, right? It says G m1 m2 over r squared. Okay, so the gravitational force on this mass, and so there's only one force acting on m. And actually, I'm gonna move the v away from here because I want to emphasize that there's only one force acting on this lowercase mass. It's the gravitational force that's acting radially inwards. So this gravitational force, G m, the capital M at the very center, and then lowercase m for the thing orbiting around, G m1 m2 over r squared. That force in magnitude has to equal mv squared over r, right? The sum of the forces is equal to the mass times acceleration. Right? That's what we're using in equation 2 right here. So we know that the acceleration is pointing towards the center of the circle, and it has magnitude v squared over r. And then the only force acting on this thing is the gravitational force, and Newton tells us exactly what the magnitude of that is. Okay. So this is great. We can, looks like we can cancel out the m's here. We can cancel out one of the r's. So it looks like v squared is equal to, I'm just going to move one of the r's over, g times capital M over r. Okay, so that's neat. It tells us how quickly the object is moving. Remember, r is the radius of the circle. It's not the radius of either lowercase m or capital M. So we want to get rid of v. Rather than taking the square root of this thing, I don't want to do that. Why don't we just square equation 1? So take equation 1 and take the square of it. So we have v squared is equal to, so I'm just looking at this whole thing and squaring both sides. V squared is equal to 4 pi squared r squared divided by t squared. And then it also equals, and we know v squared is g m over r. So remember, we don't want to involve the speed in our answer, so we're just going to set these things equal. So we have 4 pi squared r squared over t squared is g m over r. And then moving the t squareds to the right and moving the r's to the left, looks like we have this. I might write it the opposite way. So t squared is 4 pi squared. So I'm also dividing by gm r cubed. And this is exactly what Kepler's third law says. So this is great. We derived Kepler's third law. And we found out that that constant needs to have exactly this value. So this is that constant. And as promised, it depends on the mass of that body that we're orbiting, so capital M in the center there, but it doesn't depend on the lowercase m, the thing orbiting around. Okay, so this is true for this radius here, but the radius and the semi-major axis length are the same thing. So to generalize this, so that's true for like eccentric orbits as well, we just need to replace the r with the semi-major axis length, which here is the same exact thing, a cubed. So really, this is Kepler's third law. So maybe I should move this down here. So that's great. We have that constant. So your book does exactly the same logic. I just wanted to make sure we got the same thing, and it looks like we did. T squared is equal to the same constant that we got. So that's great. Okay, so obviously Earth takes 1 year to go around the sun, so we know that one. If you know either the mass of the sun or the distance that we are from the sun, you can solve for the other one. And then, of course, g is our gravitational constant. So this is great. If we know one of those two things, we can solve for the other one. Your book talks about, so Kepler influenced Newton. Kepler was able to sum up a lot of just piles and piles of papers of observations into just very succinct laws that helped Newton theorize what could be the source of those laws. Your book talks about a little bit about an analog in atomic physics with the Balmer series, and then how that helped Bohr do his model of the atom. Okay, but we don't want to go too much on a tangent, so let's move on to energy. So now we'll talk about energy of these orbits, energy. Okay, we're going to derive the potential energy from the force law. Okay, so I'm going to have, again, we're going to assume here we have a capital M just at rest at the origin, and lowercase m is going to move from some initial spot to some final spot that's farther away. Okay, so let's call this x equals 0. This is x initial and x final. And this will be our positive x direction. Okay, so we're going to imagine dragging this thing to the right. Right? You're pulling, well, I guess I don't want to imagine any other forces going on other than the gravitational force. But I'll just say that the gravitational force on lowercase m is to the left. But we're saying that this thing is moving to the right. So the work done by our gravitational force is going to be negative. And let's keep track of that work done by the gravitational force. So the gravitational force, the x component, is negative. It's pointing in the negative x direction, minus g m1 m2 over x squared. So the work done is the integral of f dot, and this is why I had my initial point at a smaller x value than the bigger one, so that our path of integration is in the dx direction, or in the I hat direction, in the plus x hat direction. Okay, so we're integrating from xi to xf. So the f is negative, so let's, so we're just plugging this in right there. I don't want to close this up too much. So we have the minus g m1 m2 over x squared dx from some initial to some final value. And we can factor this out, g m1 m2. And really we're just integrating dx over x squared, x to the minus 1. Sorry, integrating x to the minus 2 from x initial to x final. Okay, so integral of x to the minus 2 is x to the minus 1 divided by negative 1. So that turns this negative sign into a positive. This is g m1 m2. And then it's 1 over x evaluated from x initial to x final. So this is, so the work, just copying down the first line. Looks like this is g m1 m2 over x final. So you plug in the upper limit first, minus this. Now, I want you to remember that work is also equal to, the work done by a conservative force is minus the change in potential energy. So if you don't remember that, you might want to go back to when we talked about that in chapter 5, or maybe ask about that. Yeah, so this work done is change in potential energy. Minus change in potential energy. So delta U, maybe this will be a little clearer. So delta U is U final minus U initial. And so if we do minus delta U, that's going to reverse the order of these things. So U initial minus U final is equal to G M1 M2 over XF minus G M over XI. And let me write it in a way that is more suggestive. So minus G M1 M2 over XI minus G M1 M2 over XF. So see how I wrote it in a way so that it looks like U initial is this thing, maybe plus a constant because that part goes away. And then U final is this thing. So what this is suggesting is that we take our potential energy function to be minus G M1 M2 over R. And this doesn't tell us what constant we need right there, because actually when you subtract, if you find delta U, that constant just doesn't matter. So we work under the convention. It's a convention, but it's one that everybody uses. That constant is chosen to be 0. So the potential energy goes down to 0 as R goes to infinity. Okay. So your book arrives at this conclusion that the potential energy is minus G M1 M2 over R a little differently. They just say, let's start with that and prove that it works. See, I claim that this force comes from the following potential energy. So the two are definitely related. Once you start with one, you can derive the other one. You can get the potential energy up to this constant. So we'll just say that potential as R goes to infinity is defined to be 0. We require that equals 0. If you've never seen an exclamation mark above a equal sign, it means we require. Okay, so this is a different potential energy function than what we've seen before. We've seen MGH. But I still want to point out the fact that the potential energy increased in this case. So see how we took m and we dragged it this way. So just like when you take a rock and you pull it upwards, vertically upwards, you increase the potential energy, right? The work done by gravity is negative in that case. It's the same thing going on here. So if you look at this, it was some, so actually let me draw this. So u of r as a function of r is negative. It's a minus 1 over r, so it looks like this. So what we did here in this picture was we dragged this particle from some r initial. You'll notice I changed from x to r just to leave this more general, just as a radial coordinate rather than specializing to one dimension. So we had some initial r value and then we increased it. So we had some initial r value and then we increased it. So the potential energy went up, right? We went from some negative value to some smaller in magnitude, smaller in absolute value, negative value. But that potential energy still increased. Okay, if we let this mass go right here, if we just said, okay, it's not moving there and we let it go so that it could fall inwards, as it would want to do gravitationally, it's going to pick up kinetic energy. So as this thing rolls down, falls down this potential energy curve, it would, by the time it got to x initial, it would have this much kinetic energy. So whatever the decrease in potential energy was, that's how much kinetic energy you would have. Right? So this is not at all MGH, right? And I'm going to have a whole next video focusing on that fact. So saying what the connection is between this and MGH. And it'll involve talking about Taylor series a little bit. Right? So we'll hold off on that. But we are in a position to answer this question. So we're going to release, so I do want to talk about how this energy works using this formula. So this formula is a lot more general. So this formula works, this is more general. It's better to use than MGH. So this one, lowercase mgh, only works near the Earth's surface, whereas this one you should use if you're talking about radii, much different from the Earth's radius. So if you're looking at points very different from points near the Earth's surface. And that's what's going on in this problem. If the altitude is r equal to the Earth's radius, then this thing is falling a distance that's much, much, much bigger, or well, it's equal to the Earth's radius. So it's not much, much less than the Earth's radius. So we're not sticking close to the Earth's surface in this problem. Right? So we release something from an altitude r, so in other words, a distance 2r from the center of the Earth. What's the speed of the object when it strikes the Earth? Okay, so hopefully you have a picture in mind of how to do these problems from conservation of energy. So our original problem involves the Earth, and then it looks like we're dropping it from somewhere like right there, because that distance, the r, is equal to that distance, r. So maybe a little closer. Yeah, a little closer. Okay, this is our initial situation, and the final situation is when this thing gets to the Earth's surface. So just like any other conservation of energy problem, we want to start off with E initial equals E final. We only have one conservative force here, the gravitational force, and there's no energy loss to friction or anything. Right? Okay, so kinetic plus potential is equal to kinetic plus potential. And our goal is to solve for either the final kinetic energy or something related to it, right? The speed of the object. So once we have the final kinetic energy, we can get the speed pretty quickly. Okay, so we're saying we started it from rest. And what we can do now is the potential energy, we're going to plug in this for the initial and the final values. Okay, so our initial energy is minus g, the mass of the Earth, times the mass of our object, divided by, now the lowercase r here, just like before, just like with Newton's law of gravitation, this r is center to mass to center of mass. So for a spherical mass distribution, this is center to center distance. This is 2r. Remember, we have the radius of the Earth here. This is r, and then we have an additional r distance from the Earth's surface. Okay, that's equal to the final kinetic energy plus the final potential energy. So this is minus g m1 m2 divided by, and the final position is when the mass gets down here, in which case it's just a distance r from the center of the Earth. Okay, so we're going to move this term to the left-hand side. So if you ignore the g m1 m2 over r, we have negative 1/2 equals kf minus 1. So if you add 1 to both sides, you get a plus 1/2 on the left-hand side. So what I'm saying here is that it's this is equal to k final. Because you want to double check that that's true. And k final is 1/2 lowercase m is the thing that's moving, v squared, v final squared. So we can cancel out the lowercase m from both sides, multiply by 2, and take the square root to get v final is square root of g capital M divided by r. Okay, that's the answer to our original problem. So it'll depend on the mass of the Earth and the radius of the Earth, right? Not the mass of the object. Okay, so so as mentioned in the problem, this ignores air resistance, which is not a very good approximation. Most of this energy is actually lost to air resistance. Okay, so yeah, I'll hold off on the MGH discussion. I want to mention one other thing in this video, and that's escape speed. Oh, maybe two other things. So 2 more facts. I gotta be careful because this video is getting a little long. 2 facts. So 1, the escape speed is the speed to escape. Maybe that seems a little circular. Is the speed such that you could just barely escape the Earth's gravitational pull, or the gravitational pull of any object, such that the total energy is 0. E total is 0. So 0 is equal to E total is equal to the gravitational potential energy plus the kinetic energy. So if we're at the Earth's surface, if we're at the surface of a planet, we're saying 0 is equal to minus g m1 m2 over r plus 1/2 mv escape squared. So we're saying that the object is moving so fast at the surface that, yeah, it's going to slow down as you start getting farther and farther away from the planet. So in other words, k is positive, u is negative. K goes down and u goes up. But u has a limit. U will go up to this function, u of r goes up to 0. So you just need enough kinetic energy so that, like, if you're at the radius of a planet, you need this much energy to escape, to get infinitely far away. Okay, so whatever the potential energy is, so this is u of capital R, is at this particular value. So you just need whatever the absolute value is of that number. That's how much kinetic energy you need to escape. And so if you set that equal to 1/2 mv squared, you can solve for the escape speed. So it looks like that escape speed, v escape, is 2 gm over r square root. So see how in our example problem, the amount of energy here, so if we imagine this problem in reverse, like rather than dropping this thing and seeing how fast it gets, what if we launched something with that speed? How high would it get? It would just get up here. It would just get up to this spot right here. It wouldn't be able to escape the Earth. And that's because we wouldn't have launched it. So if we launch it with this speed, that's not enough. That's not as big as the escape speed. We would need a factor of square root of 2 more. So if you fire something with the escape speed, it'll escape the Earth. It'll go infinitely far away. If you fire it with only 70% of that, which is about 1 over square root of 2, then it'll reach this distance. So you need a lot of energy just to get here, and then just a little bit more to get really, really far away. That's because of the 1 over r squared force, or 1 over r potential. It really drops down as you get far away. Okay, the second fact, and then I promise I'll be done, is related to something called the virial theorem, which you'll hear a lot more about throughout physics. So I want to point out that for the circular motion especially, so you have capital M and you have lowercase m here. So this is a bound orbit. This thing doesn't have enough energy to escape, which is why it's sticking around capital M. For a circular orbit, the kinetic energy has a special value related to the potential energy. Okay, and your book goes over what that value is. So for circular orbits, and I'll write this maybe a little bit differently than the book, but it's saying the same thing. For circular orbits, if the kinetic energy is k, then we know the potential energy and we know the total energy. So if the kinetic energy is k, the potential energy is minus 2k. And the total energy, if we add up the kinetic energy and the potential energy, it looks like k plus negative 2k is negative k. So the kinetic energy is not enough to escape, right? Kinetic energy is k, but we're trapped in a potential well. So in other words, we would need 2k, we would need twice as much energy to escape. So anything going in a circle, like the Earth going around the sun, we have exactly half the amount of energy that we would need to escape the sun. Right? If you took all our energy, our kinetic energy, and doubled it exactly, if someone came and boosted us along to double our kinetic energy, we would have just barely enough energy to escape. Okay, because someone would be adding an amount k and increasing our total energy to 0. Okay, so if you're interested in this is a special case of something a lot more general and more interesting, called the virial theorem. So you might want to read about that. This is actually true. So this is true at any instant for a circular orbit. For an ellipse, this is true time averaged over one whole orbit, because obviously the kinetic energy is changing as the thing gets closer to the sun and away from the sun, etc. So you could read about that if you're interested. I at least wanted to mention it. Okay, I'm sorry that this is one of the longer videos. A lot to do though. So check out one more video for the relationship of U of R to MGH, and then we'll be done with this chapter.